So hi guys, in this video we'll discuss differentials, local linear approximation, and marginals. Let's go. So first let's discuss differentials. So let's have the function y equal fx be differentiable at a point x. So the differential dx of the independent variable x denotes an arbitrary increment or a difference in value of x, and the differential dy of the dependent variable y associated with x is given by the product of the derivative f prime of x and the differential dx. So we use differentials to estimate the differences in the value of f for a small difference in the value of x. So this statement in red can be translated into the following expression at the bottom. So given y equals fx and a small number dx, we can estimate the value of dy by the difference in value of f of x plus dx and f of x. So to illustrate the aforementioned approximation, we have the following problem as an example. So we're given the diameter of a mango tree given by this function b of t, where t is given in years, and that we know at present that the tree is 1 year old. We're asked to now solve for, using differentials, the increase in the tree's diameter after 0.1 years. So of course, we need to first find the differential dB associated with the independent variable t. So of course, looking at the formula in the previous slide, we know that we first have to find the derivative of b of t, which is -5 e raised to -t plus 10, verify that on your own, and then we multiply this entire derivative by dt, since t is our independent variable. And then take note of the values that we were given in the problem. We know that at present that the t is equal to 1, and that the difference in value of t is 0.1, since we want to go after 0.1 years. And then we get the following approximation. So we see that the b of 1 plus 0.1 minus b of 1, which is what we want to find the value for, we can approximate that value by using the differential dB, which we obtained. All we have to do now is substitute the value of dt, which is of course 0.1, and then you get this following value on the right. Thus, the tree's diameter will increase by about -1 over 2e plus 1 millimeters over the said time period. So if you input this value in the calculator, you'll get 0.816 millimeters. And then to get the true value, you only have to input the values 1 plus 0.1 and 1 into the function b of t. And then of course, you'll get the difference. You'll get 0.825, which is very close. Thus, this example shows the usefulness of differentials when dealing with problems like these. So diving further into the concept of differentials, we have local linear approximation now. So again, let's have a function y equals fx. Now let's make sure that it's differentiable at the point x0. We see here that the local linear approximation of f of x at x0 is given by this function capital L of x, and then this function is equal to f of x0 plus the derivative f prime of x0 multiplied by the difference of x minus x0. So in problems like these, you'll be given the x0. Your x is the indeterminate. That's where you're going to input the different values you'll need to evaluate. Why do we use local linear approximation? It's because it's useful in estimating the values of f near x0. So values of x that are near x0. So to illustrate this, we have the following expression. So it's similar to this one. My apologies, this f of x0 here should be f prime of x0. So this is the equation that you should be looking at. This is the correct formula. My apologies. And then as stated in this statement in red, we know that the local linear approximation can estimate the value of f of x. So to illustrate this, we'll have the following problem. So we're asked to find the local linear approximation of the following function f of x at the point x equals 50. And then using this local linear approximation, we're going to estimate the value of square root of 26. So first, let's find the derivative of f of x at x equals 50. Your x equals 50. Your 50 here is your x naught. So first, let's get the derivative, which is given by this following expression. And then you're going to evaluate 50 at this in this derivative. You'll get 1 over 20. And then recalling the formula for local linear approximation, we'll get this following expression. To get the f of 50, all you have to do is evaluate the f of x at 50. You'll get 5. We were able to solve for f prime of 50, 1 over 20. The x minus 50 stays as it is since we don't know yet what our x is. So take note that using the function that we had in the previous slide, we know that square root of 26 is equal to f of 52. So in order to estimate f of 52, we know that we have to simply evaluate the locally linear approximation at x equals 50. So in doing so, we know now that the x will be substituted with 52. Evaluating it, you'll get 5.1. And then just to check if our answer is really close to the true value, you can solve for square root of 26 using your calculator. You'll get 5.09902. So on, it keeps on going. And as you can see, it's very, very close. Thus, this problem shows the usefulness of local linear approximation when dealing with problems like these. So now we move on to marginals. Marginals is a concept that's frequently used in the field of finance, business, and economics. So we're going to apply the use of marginals in the field of economics in our specific case. But first, let's look at these common functions in economics. So first, take note that we use the indeterminate x to denote the number of units of a product. So let's have the following functions. We have this cost function, which we denote by capital C of x. And then we have the revenue function, which we denote by the capital R of x. And then we have the profit function, which we denote by capital P of x. And then we have the price demand function, which we denote by small p of x. Now let's look at the relationships between the four aforementioned functions. So you see that the revenue function is equal to your indeterminate x. So your one unit of product multiplied by the price demand function. So that's one relationship. Now we have the next relationship. We have the profit function is equal to the revenue function minus cost function. This follows from the generally well-known fact that price is equal to revenue minus cost. And then take note that the cost function evaluated at x equals 0 gives you the overhead or fixed cost. So this is the cost that you have to pay even before you create any unit of product. So always take note of these following relationships. Now let's move on to marginals. So marginals refer to the amount associated to producing an additional unit of a product. So mathematically, a marginal is just the derivative. Since you're looking for the change in a function, you're just looking mathematically for the derivative of the said function. So if you want to look, for example, if you want to look for the marginal profit, you're going to look for the derivative of the profit function in respect to x. And then follows for the other functions. So you have the marginal revenue is given by the derivative of the revenue function with respect to x. The marginal cost is given by the derivative of the cost function with respect to x. And of course, the same relationship that we saw in the previous slide also applies to the derivatives. So it's also the price equals revenue minus cost, but in this case, we're dealing with the marginal profit, marginal revenue, and marginal cost. So let's apply these, all we saw for marginals in the following problem. So a company computes that the weekly cost for creating X units of a product is given by this function capital C of X, while the revenue for selling the same number of units is given by this function capital R of X. And then both of them are given in pesos. And then we're asked to find the marginal profit at the production level of 200 units. So take note that the profit function is given by the profit, the difference between the revenue function and the cost function, as we saw in the relationships we saw in the previous slides. And then if you're doing so, you'll get the following expression if you get the difference between the two functions. And then, of course, in order to find marginal profit, we find the derivative of the profit function. So if we do so, you see that you'll get the following. If you get the derivative of p of x, you should get negative x over 5 plus 50. That's what you should get for the marginal profit function. And then since you now have the derivative of the profit function, which is the marginal profit function, and knowing that you want to evaluate the function at the derivative at 200, that's what we're going to do. So you know that the only x that you have in your function is here at the negative x over 5. So you'll have negative 1 over 5 multiplied to 200, and then you add it to 50, you'll get 10 pesos. Yeah, I think that's it. Thanks guys for watching.